Welcome back. We're going to look at one more example of this, and it's important that you watch this because there are some more things sort of to be elucidated from looking at another example. So here we have a reaction, okay? And if we thought that the mechanism, this is the overall reaction, if we thought that the mechanism of action was NO2, colliding into CO, we would expect the rate law to be K times the concentration of N2, first order, because there's no number here, and carbon monoxide, or CO, to the first order, because there's no number. But it turns out that the actual rate law, when you look at experimental evidence from what we've been doing recently, it turns out that this is the actual rate law, where CO is zero order, that's not in the rate law, and NO2 is second order. So this must not be the mechanism. There must be a different mechanism, not just NO2 colliding into CO. So we're going to take a look at what's actually happening. So this is the proposed mechanism for this reaction. And we see in the first step, two molecules of NO2 collide, and they produce a molecule of NO3 and a molecule of NO. And we see that NO is one of the products. Then this molecule of NO3 acts in a second reaction where NO3 collides with CO, producing a molecule of N2 and CO2. Now, if we look at, and then again, to make sure that this is right, this mechanism is a good mechanism, we would have to make sure that it actually adds up to this one. And we'll see that it does, these cancel, the intermediates cancel, and then it adds up to the overall reaction. But again, for a mechanism to be right, it has to add up to the overall reaction. And we notice that here, the slow step is first. Okay? So there's some question here. So what is the intermediate of this reaction? So if we take a look, what is the thing that is being made and then used up in the second step? Well, this is made in the first step and used up in the second step. So this is being made in the first step and then used in the second step. So that's the intermediate of this reaction. Okay? Now, what is the rate law? So remember we said that rate law is determined by the slow step as long as it's first, and we're going to look at examples of when it's not first, what happens. So the rate law, in this case, which I need to, hopefully my mouse will work this time. I'm home now, so we'll see. Pen. Yeah, it's going to work. So the rate law, okay, would be equal to the rate law of this elementary step. So that would be rate, which I'm just going to write as R because I don't feel like writing, is the concentration, and it's really hard writing without a smartboard marker, NO2, close the parentheses because we need to, raised to the second power because there are two of them. So that would be the rate law in this case, which is what we saw, which is what was the experimental rate law here. Okay. Okay. So a little bit more about intermediates here. So NO3 is an intermediate, and like we said, is a substance that's formed and then used up in the next step. Okay. Intermediates are less stable than reactants. Okay. But they're more stable than the activated complex, which is that thing on top of the activation energy. And intermediates have normal bonds, like they're not extremely unstable. You can collect them and isolate them. Unlike activated complexes or transition states, which cannot usually be isolated. So again, if we look at our potential energy diagram, okay, let's just go through this one more time. We'll see that we have, for the first step, we have a big hump, or big activation energy, and that's because this reaction is slow. Okay, so again, the energy needed for these to collide and the orientation needed for them to collide is complicated and a lot. So it has a large activation energy. This is the intermediate, right? And the intermediate is in this valley between the two activation energy hubs. Now also remember at the top, we have the activated complex, which is just about, like, sort of like when these are about to collide is the activated complex. Okay, and that is very, very unstable. Okay, and then if we look at, for the second step, we have a smaller hump. Okay, this is the fast step, so it has less activation energy. And that's why the hump here is lower. And again, just looking at this reaction, we have H being less than 0, so this reaction is exothermic, so the products end up being lower than the reactants because energy is released. Then with this activated complex thing, again, it's like sort of when these two are about to react, you know, when they're in between bonds breaking and bonds forming, that's the activated complex. And then the intermediate, which is stabler, has more stable than this because it's lower in the graph, sort of is in this valley here. So, if we look at the one more mechanism for this reaction, okay, which we just saw, is this a valid mechanism? And these 3 criteria have to be met. The elementary steps have to add up, and they do. We can cross out things and see these would be crossed out. So we'd have one of those left, and this would be crossed out. And then they would add to the original reaction. The mechanism does correlate with the rate law, which we just saw, with this being KNO2 raised to the second power. And the steps are reasonable. There are no tetramolecular steps here. They're only bimolecular, so there's no crazy elementary steps that are unlikely to occur. So this reaction, or this mechanism, meets the 3 criteria. Okay, now, so this is a summary point, and then, so if the slow step occurs first in the mechanism, then it's the stoichiometry of that step that determines the rate law. Okay, we're going to see, I think, Wednesday, either through a video lesson or in school, what happens if the slow step is not first. And that makes it a little bit more complicated. All right, have a good snow day.